Reaction Rates Part 1, so Lecture 15. So now we're going to move away from talking about molecules and solids and liquids, and we're going to start going back to this idea of chemical reactions. Last semester we spent a long time talking about if a reaction will happen using the thermodynamics, enthalpy, entropy, Gibbs free energy. Now we're going to start looking at how quickly reactions happen, or the speed at which reactions happen using kinetics. So if we look back, thermodynamics, as we just said, is does a reaction take place? Is there a reason that the reactants are going to combine to form products? But that doesn't necessarily say how fast the reaction is occurring. So we know that graphite is diamonds, are going to convert into graphite. That reaction is thermodynamically favored, right? It's spontaneous. But what it doesn't say is how quickly that reaction occurs. And in fact, it occurs very slowly. The kinetics of the speed of that reaction is very slow, which is why we say diamonds last forever. In this chapter, we're going to actually begin talking about these reaction kinetics, or the reaction rate. And we define reaction rate as the rate of change in concentration of a reactant or product with time, given units of molarity per second, or per unit time. Typically it's second because that's our SI unit. So if we look at the reaction of A goes to B, then this rate of the reaction that's going to occurring is going to be the change in concentration we see of A over some time period delta T. Right? And if you'll notice, this rate's going to be negative because that's decreasing, so the final minus initial, if we just did that change, that would be a negative number. To make that rate positive, we're going to see we need that negative. Right? The change in concentration per time. We could also talk about the rate of appearance of B as being the change of concentration of B over some unit time. Right? And since A decreases in time, like I said, then that's going to be negative. So let's look at this reaction actually over time. So here in this figure, we can see that we start out with all A, and as the reaction proceeds in time, going from this side over, we see that we get more and more B, more and more of these red dots. So we can follow the concentration curves down here. We see that the concentration of A as time goes on goes down, the total number goes down. At the same time, the number of molecules B goes up, which is dictated by these rate equations. That we can monitor the rate that A is disappearing because it's the negative change in concentration of A divided by however much time we're following this reaction. Or the rate of appearance of B is the rate of concentration change of B over the change in time. That's what we're talking about there. Right, there's several factors that are going to influence the rates that these reactions occur. Right? And the first and foremost is that in order for a reaction to occur, the two particles must collide. Right? So we have to have two molecules or atoms come together and impact each other, and that is what, only if they collide can we have the possibility of a reaction occurring. Right? And we see that as this concentration increases of that reactant, there's a greater likelihood that we're going to get collisions, which means that at a higher concentration, typically we get a larger reaction rate. Because the larger number of particles is going to give us a larger possibility for collisions. And the physical state, the state that they are in, actually plays a role too, or influences. The two solutions must be mixing in order for those collisions to occur. So the substances must mix, must come in contact, again, they have to collide in order for these reactions to occur. So that typically happens when we have two, that they're in the same state. We can have some reactions occurring at a surface, that is true, but the rate is going to be fairly low because we have to have these collisions again. And typically the higher the temperature, the higher the reaction rate. Remember that this energy, or this temperature, gives us an increase in temperature, gives us an increase in kinetic energy, which means that the molecules are going to be moving faster, so the more likely to bump into other molecules. So the higher temperature gives us higher energy, therefore more collide, and more will collide correctly in order for this reaction to occur. So when we're talking about these, what we're really talking about is on the atomic level or molecular level. Those two have to come together with sufficient energy and in the proper orientation for this reaction to occur. But it always comes back to this fact that they must collide. So let's look at another example. Instead of A to B, let's look at our actual reactions. We can look at bromine plus the formic acid. Right? This takes us an aqueous solution, which is orange, brown, and as it goes away, as that bromine molecule, Br2, goes away, our solution is going to become clear. We can see that we get this reaction versus time. Right? So we can talk about the rate of this reaction is occurring over a variety of different things. We can talk about an average rate, which is sort of what we talked about before, the rate, the amount of change in concentration divided by the amount of time we want to average that. Right? So that would be a point up here on the graph versus a point down here. We can also talk about an instantaneous rate, which is equivalent to the tangent of this line. Right, where it's the rate at that specific time. Much smaller time frame, going to be and we will see that these instantaneous rates are going to vary as the reaction occurs. But overall, we're going to get this average rate. Right? And we can also talk about the initial rate. It's not on this slide, but the initial rate is just the rate that the reaction occurs at the very beginning, at time 0. Right? Which is an instantaneous rate. We just fix the time at 0. Because these reactants and products are stoichiometrically related, we can then stoichiometrically relate their rates. Right? So if we look at a different general reaction, 2A goes to B, that means that 2 moles of A are going to disappear when each 1 mole of B is formed. So we can say that the rate is going to be the same. Right? The rate that's occurring is going to be a negative 1/2 the change in concentration A over change in time. That same rate is going to be equal to the change in concentration of B divided by the change in time. Right? So that stoichiometric relationship, just like we converted before, we have a molar ratio here. 1 mole of B gives for 2 moles of A. If we break this into a general reaction, such as to the bottom here, then we can say this rate of reaction is going to be equal to, so AA plus BB goes to CC plus DD. Then the rate of the reaction is the negative 1 over A, little a, times the concentration of change of A per unit time, which is equal to the negative 1 over the coefficient B times the change in B over the change in time, which is equal to 1 over C, change in C, change in time, which is also equal to 1 over D, delta D, change in concentration over time. So we can use this molar ratio, just like we have in all the other reactions, to relate not only between those, but through this idea of rate. So we can convert to the rate of anything if we know the rate of change of one species. We'll also see that if we follow those reactions, if we follow these reactions, that the rate is proportional to the concentration of that reactant present, but it's not directly proportional. There's some probability factor or some fudge factor, some constant that relates the rate that that reaction is occurring to the concentration, which we're going to call the rate constant. So if we look at a whole bunch of instantaneous rates here, versus the concentration of bromine present for that reaction before, we see that if we take the rate that the reaction is occurring divided by the concentration present, we get a constant. And that constant is this proportionality factor of this, what we're calling the rate constant. So this is going to come into play later when we talk about discussing rate laws, but there's also, remember, the rate isn't directly equal to the concentration. There's some proportionality constant there, which we call the rate constant.